Okay, so this is the overview of the silicates. Now we will go to one by one the different prominent groups such as olivine, feldspar, like that, and then we will understand how these major families of minerals looks like. Okay, so I'll just take a 2 minute break and then I'm coming back. Okay, let's start with olivine group. So olivine has the general formula of it can have anything in the first site, that is MgFeMnCa, magnesium, iron, manganese, calcium, then two SiO4. Okay. SiO4 is the tetrahedra with any one. Remember, olivine is a island silicate. Okay, right? It's an island silicate or a nesosilicate. So we are studying on a nesosilicate, that is olivine, having MgFeMnCa in the interstitial site twice, then SiO4 tetrahedra. The structure is isolated tetrahedral silicate, blue in color in picture. Okay, these are the tetrahedras of olivine. And individual tetrahedra linked by divalent cation, golden spear. So these are the cations present as ionic bonds in the interstitial spaces. It can be Mg, Fe, Mn, Ca, anything. Okay. The crystal system is orthorhombic. Remember, olivine forms orthorhombic crystal system. And then there is composition. So the end members. Here is a diagram showing the different end members. Of end members means the different. See, this one has calcium. This is a calcium olivine. Okay, or larnite. Okay, then this is monticelite. It has both Ca and Mg. So in this diagram, this Ca and Mg, Forsterite and larnite, is the end member. End member means last member, whereas this one is in between, right? Which has both Ca and Mg, monticelite. Similarly, this one, cachetonite, which comes between Fayalite and Larnite. Okay, this is how it is. And these two forms complete solid solution. Complete solid solution. Complete solid solution means any rock can have some percentage of Mg and some percentage of Fe. I'll explain it to you in later. And this natural olivines, so natural olivines are usually solid solution of Fayalite and Forsterite. So mostly Fayalite and Forsterites are found with minor other compounds such as tephroite and larnite. Larnite here, and tephroite is Mn. Mn does not comes under this one. Okay, tephroate and lanite are rare olivines. Okay, mostly we get Forsterite and Fayalite. Forsterite and Fayalite. So this is a solid solution showing Forsterite and Fayalite olivine solid solution where the melting point of Fayalite is 1205 and Forsterite is 1890. So I'll just try to explain how this solid solution looks like, because if I try it now, I think you will get a better idea when I really go into all these things in igneous petrology class, because we will again come across this eutectic system, solid solution system in igneous petrology. So I think it is better to give you a brief idea right now using the phosphorite phyllite solid solution, so that you can understand it in a better way. So just give me a moment, and then I'll open up my whiteboard and I'll try to explain it to you. So I will be explaining you the phosphorite phyllite solid solution. First, I'll explain it to you in a 2D manner. Then I'll try to explain it to you in a 3D manner. Okay. So let's start with the bar. This is a bar. This is phosphorite, and this is Fayalite, right? This is Forsterite and this is Fayalite. Mg2SiO4, this is Fayalite, Fe2SiO4. So what happens is these two are the end members of this bar, right? So if I find a rock which is here, so it will have 100% Fayalite, that is 100% will be Fe. So it will have a structure like this, where these are the tetrahedras, and these are the interstitial cations of Fe only, iron only. Interstitial cations of Fe only. No Mg will be there. If I find a rock which is from here having 100% Fayalite. But if you find a rock from here having 100% Forsterite, that is Mg, that means the same thing will be here, happen here, with different tetrahedra of SiO4 and interstitials of only Mg, only Mg. Okay, but if we find, so this will be, let me remove this. So this will be 100% FO, this will be 100% Fa. Now any rock if we find here, okay, so what will be the composition here? Since this is 100% Fa, this is 100% FO, that means here it is 0% FO, and here it is 0% Fa. So 0% Fe is here and 0% Mg is here. That means if I find any rock here, say this is 80%, 80% FO. So what will we have? We have 80% FO and 20% Fa, right? So in this rock, we will have tetrahedra, and then we will have all these cations, where 80% of these cations will be, and 20% will be, 80% will be phosphorite having Mg concentration, Mg2 plus will be Mg2 plus, and 20% will be Fe2 plus, right? Very simple to understand. Now just tell me what will be the composition here. So this is 70%. 70% what? 70% Fa, right? I'll just give you 1 minute. Just tell me what will be the percentage of FO. It's very simple, right? This will be 70% of iron will be there and 30% of Mg will be there. Simple. So this is in 2D. In 2D, how we can simply explain a solid solution. Now let's come to 3D, where we can understand it in a better way. So if we are drawing a 3D, you have to draw it like this. This is a two component solid solution curve. Okay, remember this is a two component solid solution curve. If you are drawing this, remember it is very good if you can remember the the melting points of Fa and Fo. But if you don't, just write it like this: 1900 degrees Celsius, just below mark this point, and this point just below 1300 Celsius. This is the temperature, and this is the composition. Say same thing that I have just drawn in 2D. This is the Fo, this is the Fa, right? This is the Forsterite, this is the Fayalite. Fine. Now what are these things? Okay, this line is called solidus. Solidus. Whereas this line is called a liquidus. Right? Liquidus. This is called solidus, this is called liquidus. Any point, any rock, or any, you can say melt, here it is liquid. This phase, this phase, this phase is liquid. Okay, this phase is liquid plus solid, whereas this phase is solid. So what it means is, actually, if we take a sample from here, from this liquidus part, we will have a complete melt. Melt means complete lava will be there here. Okay, if we take it from here, say this is A, this is B, this is C. If we take sample from here, B, this one is A, this is B. B will have what? B will have both liquid. Liquid means melt. Melt means lava. We'll have both lava, magma, and lava. This is burning, very hot temperature, burning lava. No crystals has formed, right? I'm trying to explain it to you in a very layman language, okay? And this is a semi-cooled sample having both lava, magma, as well as some crystals in it. Now, to see, let's say we take a sample from here. So what will it be? It will be no lava will be present, or no melt, no magma will be present, but only crystals will be there. So only crystals will be there. Fine. I hope you get it now. Okay, so this will be only liquid phase. This will be liquid as well as crystal phase B, and C will be total solid phase. Fine. Now what happens, actually, why we need this diagram is actually to understand how things will work. Say this is 80, this is 50, and this is again 80. This is 80 Foster, this is 80 Fayalite, this is 50-50. Okay, now say we have a melt here. We take a melt here, and we will understand the cooling history of the melt. The cooling history of the melt. So what will happen if the melt is here? It will slowly lose temperature. Say we are crystallizing the melt, and we are trying to observe how this melt or this magma will crystallize different minerals out of the melt. So what will happen is this melt will lose temperature, and then will come directly. This is losing temperature, right? This is increasing temperature here upward, and this is losing temperature downward. So this will lose temperature and then hit the liquidus curve, right? This will hit the liquidus curve as the temperature will reduce. So in the liquidus curve here at the first, at this point only, the first crystal will start to form. The first crystal will start to form, or the first mineral will start to form from the liquid melt. Okay, the first crystal will start to form from the liquid melt. And if we want to know the composition, if we want to know the composition of the first melt, we will find it using, if we project this thing here, the horizontal line is projected here, and then bring it down here, then we will be able to understand what is the composition of the first mineral that is being crystallized after hitting the liquidus. So here at this point, the melt composition is this. The melt composition is this. Say this is say, sorry, looks a little bit odd, but say, so this is 50, and this is say the melt composition is actually 60. 60 Forsterite and 40 Fayalite, the melt composition. But the first mineral that has been crystallized here can be identified using this graph here, that is Forsterite 90, Fayalite 10 is the crystal that is being crystallized. First crystal that is being crystallized is of the composition of Forsterite 90, Fayalite 10, whereas the melt that just hit the liquidus curve is of the composition Forsterite 60 and Fayalite 40. Okay, now where will it go? It will then follow this liquidus. After hitting the liquidus, it will follow the liquidus curve as the temperature will decrease. So say it follows the liquidus and comes here. Again, the melt composition will be this. Melt composition will be this. Whereas the crystal composition of the mineral that comes out from it have the composition of this. Say Forsterite 70, Fayalite 30. Whereas the melt composition will be, say, Fayalite 70, Forsterite 30. Just the opposite. Fine. Then again it will come here like this. It will come here and here and here. Okay. So this, where it will end, it won't go here. It won't go here. Okay. It will end where? Oh, sorry. It will end there where it have the, say, it goes up to here, where we are getting the last composition similar to the melt composition, where we are getting the last mineral similar to the melt composition, right? This is the melt composition. Is the melt composition similar? Then here the melt will stop, and all the melt will crystallize, and last mineral to crystallize from the melt will have the same composition of, say, Forsterite 60 and Fayalite 40. Okay, so what will be is the first melt, it comes here in the liquidus, touches the liquidus, the first mineral to form we can get it using, if we just project it here at the solidus curve, then drop it down, we will get the mineral as assemblage of the first mineral crystallizing. Then the melt will come here, right? Will follow the liquidus curve. So if you want to find the mineral assemblage of this point, then we'll just extrapolate it here at the solidus curve, then just extrapolate it downward, we'll get the mineral assemblage, and the last melt will come here. We'll extrapolate it to the same position of the melt, right? Then it will be, you will put it downward, and this is the final melt, final mineral to crystallize from the melt, which will have the same composition. Remember, the final melt, the final crystal that crystallizes from the melt will have the same composition as the initial composition of the melt. Okay, and this will end the whole journey of the melt, and the final crystal will form, right? So this is the basic idea of how a solid solution curve works. So this is an example of a two component solid solution in olivine system using Forsterite and Fayalite solid solution. I hope you understand. Thank you. Okay. Now coming back to our topic. So this is the diagram that I was talking about. Now you know how this crystal melt thing works. Now showing temperature and composition of Forsterite and Fayalite in olivine solid solution. Fayalite melting point is 1205 and Forsterite is 1890. Okay. So I have just told you the how we can crystallize from a melt. Okay. The same thing can happen if we want to melt a crystal, right? The opposite, just opposite. If you want to crystallize from a melt, and if you want to melt a crystal, okay, that is also can be can be demonstrated using this diagram, but that is of a different topic. We will study all those things in igneous petrology class. Here, okay, so olivine is primarily an igneous mineral crystallizing from high temperature magma, occurs predominantly in mafic and ultramafic rock. Remember, it is olivine is usually the first crystal that forms from a uh, combined magma of different, say, different elements and different molecule composition. I'll just give you a Bowen's reaction series. From that, you will be able to understand how which mineral to crystallize first from a melt, right? So the general, so Mg rich olivine is never found in silicates rock, but Fe rich olivine is occasionally found in granite. So Mg rich olivine is mostly a mafic. Mg means mafic. Uh, Mg not means mafic. Mg comes in mafic, but Mg rich mineral, Mg rich olivine comes under mostly mafic rocks, but Fe rich olivine can be found in granite, that is in siliclastic rock. So olivine maximally happens in, basalts or mafic rocks. Mafic mafic rocks. So I'll just give you a Bowen's reaction. Which mineral comes first and like that. So this is the Bowen's reaction series where temperature is decreasing. Temperature is decreasing. So we can see it like olivine, then pyroxene.